So we'll go ahead and get started on this. So hopefully you guys had a chance to watch the video over the weekend. Otherwise, you might be just a tad bit lost here. But we're going to start talking about, just go a little more in depth about equilibrium, and this is the first day that we're actually going to talk about ice tables, so that'll be fun. If I had been a little more prepared, I would have been playing Ice Ice Baby when you guys walked in. I'll probably do that in class. Alright, so heterogeneous equilibria, we want to talk about how this happens. I mean, heterogeneous, do we remember what that means exactly? Versus homogeneous. Okay, so it's a solution where really you can actually see the parts. It's very obvious that it's a mixture. And so heterogeneous equilibria is one where we've got some of the reactants and products are actually in different phases. So some of them might be solid, some of them might be liquid, some of them might be gases. And so that's a heterogeneous equilibria. So an example of this, you've got calcium carbonate, which is a solid, and it's in a reversible reaction with calcium oxide and CO2 gas. Okay, so you got two solids there and a gas in that reaction. So that's called a heterogeneous equilibria. So if we were going to write the equilibrium constant for this reaction, the way that I have taught you to write the equilibrium constants, it would look like this. Now I put that prime there because that's technically not the right equilibrium expression, but that's what we would think that we would write at this point. Okay, so we need to talk a little bit more about why we don't write it exactly that way. Let me get this out of the way. Hopefully you can see this. So the thing is, talking about the concentration of a solid, kind of a weird thing, right? Because usually when we talk about a concentration, we're talking about the concentration of something, usually like a solid in a liquid, and we talk about the molarity. How many moles of solute do we have per liter of solution? Well, a solid, it's just, it's just a solid. So if I ask you, what's the concentration of copper? That's kind of a weird question, right? I mean, it's copper, right? And copper always has the same density. You can kind of think of density as a concentration, right? But at any given temperature, the density of copper is always going to be the same. So if you actually wanted to calculate the concentration in moles per liter of copper, it would always be the same, right? Because I'm starting with grams per milliliter. That's the density. And then I could do a little dimensional analysis here to figure out 141 moles per liter. Okay, but that's always going to be the concentration of copper solid. Okay, now if I do something where I end up with copper 2+ ions dissolved in water, now we can talk about the concentration of copper 2+. But the concentration of solid copper, that doesn't really make sense. Okay, it's always the same. It's kind of a constant. And then same thing with a liquid. Right, if I have a pure liquid and I ask you what's its concentration, again, that doesn't make a lot of sense to talk about it that way, okay? Because it's just, the density of water is 1, and if there's nothing else in that water, if we're just talking about the concentration of the water itself, well, it's just 1 gram per milliliter, and then if I figured out the molarity of that, it would be, it would always be the same, okay? So that's kind of the idea. With a solid and a liquid, its concentration is not going to change throughout the course of a reaction. It's kind of a constant thing, okay? So, hopefully you can see that. Pure solids and pure liquids are always going to have the same molar concentration, no matter how much of it we have. So it doesn't matter how much copper you have. You can have just a tiny bit of copper or a lot of copper. It's always going to have the same density, okay? In its solid form, its concentration does not vary. And so we're going to call that a constant. And that means that it's not really used in the equilibrium constant equation. Okay? So the bottom line here is that we don't include solids or pure liquids in our equilibrium expressions. Okay? And that's basically what you have to remember here. That's going to be very important because you'll see these heterogeneous equilibria a lot, where you've got a solid on one side of the equation and you just don't put it in the equilibrium expression. Okay. So that reaction that we saw before, the actual equilibrium expression for that, in terms of concentration, is just K equals concentration of CO2. All right. Because if you look back over here, calcium oxide and the calcium carbonate, those are both solids, so we don't put them in the equilibrium expression. Okay, so all you're left with is K equals CO2. Okay, so now this is our final form. Now if we wanted to write that in terms of pressure, Kp equals the pressure of CO2. Because CO2 is a gas, so we can write that as a gas equilibrium expression as well. And hopefully, in the last set of notes, the relationship between these two things kind of made sense. We'll talk about that in class again today. All right. In both cases here, the equilibrium constants don't depend on the CaCO3 or CaO, as long as we have some present at equilibrium. Okay, as long as it's not all used up, then it's going to stay constant. Sorry, I know these notes go all the way to the bottom here. Okay, so that's that. Again, just, showing how this works. If I've got a whole bunch of CaCO3 and just a little bit of CaO at equilibrium, versus having just a little bit of CaCO3 and a bunch of CaO at equilibrium, as long as we have some of each, they don't really affect the equilibrium. Okay, so it's just constant. Okay, and the concentration of these things doesn't change because it's just a pile of solids sitting at the bottom. Okay. All right. So now we need to talk about calculating the equilibrium constant, and this starts out really, really, really easy. Once you know how to write the equilibrium expression, if they give you all the equilibrium concentrations, all you have to do is just plug it in. Okay. And so, like I said, this starts out really easy here. An example of this, let's see, we've got a mixture of hydrogen and nitrogen in a reaction vessel, and it's allowed to attain equilibrium at 472 degrees Celsius. And then it's telling us the pressure at equilibrium for all of these things, okay? And from this, we want to calculate the equilibrium constant for this particular reaction, okay? So I'm going to calculate the equilibrium constant in terms of pressure, because that's what we're given here. All right. So first off, how would we write the equilibrium expression for this reaction? Let's check one thing first. Do we have any solids or pure liquids in our expression? Okay, so these are all gases. By the way, I should just say this, just to make it very, very clear. The things that do go in your equilibrium expression, gases and aqueous solutions, okay? Those are the two things that you are going to put in your equilibrium expression. Solids and liquids do not go. So since these are all gases, they all go in our equilibrium expression. So we would write Kp equals, and I'm going to write this in terms of pressure. So the pressure of NH3, what do I have to do to that NH3? Okay, and this is going to take some getting used to, because in the last chapter we said that you can't write a rate law based on the stoichiometry, okay? But you can write an equilibrium expression based on the stoichiometry, okay? So that's fun. So then we divide that by its products over reactants, okay? So we divide that by our two reactants. So we've got, I'm sorry, this is really squished in here. Pressure, the N2, to the first power, because that has a coefficient 1 in front of it. And then the pressure of the H2 cubed, because of the coefficient 3. Okay? So that's our equilibrium expression, and then we just plug in the numbers that they've given us here. Okay? So our Kp equals, let's see, our NH3 is 0.166. And I guess we can keep track of our units here. K should be a unitless number. Let's see, the pressure of the N2 is going to be, where is it? 2.46. It's not going to be here. Trying to remember exactly why that's the case. And the H2, 7.38. Okay, so then once we calculate this, that should give us our answer. Oh, thank you. Yeah, that's cute. That's weird. Okay. So then once we calculate all that, I need to find my calculator here. Yeah, see, when they're working this out in the book, they're not including the units with their numbers. I'm going to have to look up that again. I don't remember exactly why the units don't get included here. Just remember that your K, your equilibrium constant, it doesn't have units with it, okay? Yeah, it's kind of a nice change, right? Divided by... divided by... 0.38. Whoops. Okay, I'm getting 2.79 times 10 to the negative fifth. Okay, and that's our equilibrium constant. Okay? Now, just a little bit of review here, okay? Because I want to make sure that we understand from the video that we watched last time what this is really telling us, okay? So remember, an equilibrium constant basically tells us once this thing levels out, okay? Now, again, let's just review this. What does it mean when something's when an equation or a reaction is at equilibrium? Okay, so in this particular case, you've got the reactants are changing to the products at exactly the same rate as the products are changing to reactants, okay? So it's going back and forth at exactly the same rate, okay? Now, does that mean there are equal concentrations of each thing on each side? Okay, no, usually not, okay? So if we look at this equilibrium expression right here, this is a small number, right? Now just look at our expression that we just wrote, okay? It's products over reactants, right? So if this is a small number, then what has the higher concentration, the products or the reactants? The reactants have a higher concentration. Okay, what that means is, at equilibrium, there's going to be a lot more of the nitrogen and the hydrogen gas than there will be of the ammonia gas, okay? That's just the way it works at equilibrium at, what temperature are we at? At 472 degrees Celsius. That's the case, okay? Now, at different temperatures, different pressures, could be different, okay? But that's what it is at 472. Okay. Now here's where it gets a little bit harder. If we don't know the equilibrium concentrations of all the things in equilibrium, then we have to do a little bit of figuring here, okay? And in this case, we use what's called ice tables. Now I think next year I might introduce ice tables a little bit earlier in the year because I think they're useful. We have kind of sort of talked about them a little bit already when we were talking about our reactions in aqueous solutions unit, but that was a really long time ago, so I doubt that's really fresh in your mind. But ICE stands for initial concentration, change in concentration, and equilibrium concentration, right? So we're going to make a table where we figure out what are our initial concentrations of our reactants and products, okay? And then we're going to figure out what is the change in concentration that happens, and then we're going to figure out what our equilibrium concentrations are, okay? So here's an example. And of course, I don't have any room on here. Oh, okay. I actually have a nice little chart on that one. Okay, so here's the example. We've got enough ammonia dissolved in 5 liters of water to produce a solution that is 0.0124 molar in ammonia, okay? The solution is then allowed to come to equilibrium. Analysis of the equilibrium mixture shows the concentration of the OH minus is 4.64 times 10 to the negative fourth molar. Okay? Alright, so when we do these ice tables, we want to use molarity. Okay? And so that's the way that we're going to plug these things in here. Let's see here. So basically what we want to do is we want to just sort of figure out our setup as far as what we're given, okay? So first of all here we're given 0.0124 molar is, well, what is that? Is that an initial concentration? Is that a concentration at equilibrium? What is that exactly? Okay, so it says enough ammonia is dissolved in 5 liters of water to produce a solution that is, so there's the molarity of ammonia. But look at the next sentence here. The solution is then allowed to come to equilibrium, right? Okay, so this is actually an initial concentration, not an equilibrium concentration. And then it says analysis of the equilibrium mixture shows the concentration of the OH minus is 4.64 times 10 to the negative fourth. So this is an equilibrium concentration, right? Okay, so those are the only two things that we're given here, and we want to calculate the equilibrium constant. Okay, so that seems like maybe not enough information. One thing that might be good to do right off the bat is just write the equilibrium expression for this reaction. Okay, so if I was going to write that, and I'm probably going to write this one in terms of concentration, so I'll just say K. You don't always have to write KEQ or KC or KP. If you're doing it in terms of pressure, it's probably a good idea to write KP, but otherwise you can probably just write K. Alright? So, what is our equilibrium expression here? Okay, so we've got NH4 plus times OH minus, sorry, I know this is difficult to see, divided by what? NH3. Well, what about the H2O? Oh, it's a pure liquid. Okay, so it doesn't go in our equilibrium expression. Okay, so watch out for that. So there's our equilibrium expression, right? Now, we only know one of those three things at equilibrium. That's what's making this a little bit difficult, okay? But we can figure this out. So, what we're going to do here is we've got one initial concentration that we know. And so notice how I've kind of set up this table, okay? And do you guys have this set up on your... Okay, you don't have this. I would draw this chart just like this, okay? And basically what you've got here is each box corresponds to a particular reactant or product, okay? So you've got your columns set up like that, and then you've got your I, C, E rows here, okay? Which makes your ice table. Now, for our initial concentrations, let me go back here. This is our concentration of ammonia, right? Our initial concentration, 0.0124. What's our initial concentration of water? Well, that question doesn't really make sense, right? I'm asking you the concentration of a pure liquid, right? That's why it doesn't go in our equilibrium expression. So it doesn't need to really go in your ice table either. Okay, so what I would honestly do, anytime you have a solid or a liquid, just X out the box. Okay, we're not going to use that. Alright, now let's see if we can figure this out. What are the initial concentrations of NH4 plus and OH minus? No, they don't tell us that, but maybe we can figure it out. Because I'm starting out here by dissolving NH3 in the water, right? So is it fair to say that at the very beginning of this thing, before the reaction ever even starts, this is all I have? The NH3? Does that kind of make sense? Okay. So our concentrations of these two things are actually 0 to start out with. Okay? Alright, now, here's another very important thing that I'm going to say. The change row. This is where you use stoichiometry, okay? You do not use stoichiometry any other time in these ice tables except for in the change row, okay? This is it right here. This is where you use the coefficients in the equation, okay? And this is the only place where you can use the coefficients in the equation, okay? Because we can tell if one thing changes by a certain amount, we can tell how everything else changes, okay? So let's look back over here at what they're telling us. Alright, they're telling us the concentration of the OH minus at equilibrium is 4.64 times 10 to the negative fourth, okay? Let's go back over here. So the equilibrium concentration, 4.64 times 10 to the negative fourth molar. Doesn't completely fit. So, what was the change in the OH minus concentration? It was this, right? Okay, so it changed by plus 4.64 times 10 to the negative fourth molar. Okay, looking at the stoichiometry, because again, in this row right here, we can pay attention to the stoichiometry. For every 1 mole of OH minus that gets formed, we have 1 mole of NH4 getting formed, okay? So this is going to be exactly the same, plus 4.64 times 10 to the negative fourth molar. Okay, here's the tricky part. This is a 1-to-1-to-1 stoichiometry, right? So if these are increasing by 4.64 times 10 to the negative fourth, then the NH3 is decreasing by 4.64 times 10 to the negative fourth. I should label that M. This is going to help us get our other equilibrium concentrations, right? Because this one started at 0, so now we also have 4.64 times 10 to the negative fourth molar of this. And then we have to take this starting concentration here, this 0.0124, minus the 4.64 times 10 to the negative fourth. And I'm getting 0.0119. Is that sig? Yeah, that's right for sig figs. 119 molar for my ending concentration of my NH3. Okay? So now, we just figured out all the equilibrium concentrations, okay? So then we can plug that back into our equilibrium expression. K equals, let's see, it's these two things on the top, right? So 4.64 times 10 to the negative fourth times 4.64 times 10 to the negative fourth, which you could just square that. I don't have to write that out twice. I just did see, you would see it's coming from both of these reactants. And then we divide that, or sorry, both of those products. And then we divide that by the reactant, 0.0119. And that should give us our equilibrium expression, or equilibrium constant. Okay, so 4.64 times 10 to the negative fourth squared. Divided by 0.0119 gives me 1.81 times 10 to the negative fifth. Make sense? Okay. It's a little bit of a lengthy process, but hopefully not too bad. Let's see. Alright, so just want to kind of step back for a second here and talk about the things that you can use the coefficients for, okay? Coefficients in a balanced chemical equation, first and foremost, they will tell you a mole ratio of reactants to products, okay? We've known that for a long time. They also tell you a concentration ratio, okay? Which sort of just took that for granted because we have talked about that already this year, but I just want to make sure that you guys get that. We were doing this in terms of concentration, our stoichiometry right here, and that's okay as long as you have a solution with a constant volume, right? Which in this problem at the beginning of it, it's 5 liters, right? Okay, and that 5 liters of water, we're assuming that that volume's not changing, okay? So as long as the volume doesn't change, then you can use your concentrations as a mole ratio, okay? Or you can use the coefficients to tell you the concentration ratio. It can also tell you a pressure ratio as long as the gas is at constant temperature and constant volume. Okay, so you got to check that. We talked about that in the gas unit. Okay, and they will also tell you a volume ratio for gases when they have a constant pressure and a constant temperature. And again, we talked about these last two in the gases unit. Okay, so there are a lot of things the coefficients can tell you if there are some things that are held constant. All right. I would say these two right here, well, really these three are probably the most important for this particular chapter, okay? The coefficients tell you a mole ratio, a concentration ratio, and a pressure ratio. There's equilibrium arrows. Okay, consider the following reaction at 600 degrees Celsius. I don't know why there's an underline on that degrees sign. I was being silly with the notes here. So here's our reaction, okay? In a certain experiment, we've got 2 moles of SO2, 1.5 moles of O2, and 3.0 moles of SO3. Those are placed in a 1-liter flask. At equilibrium, we've got 3.50 moles of SO3 present. So we want to calculate the equilibrium concentrations, the O2 and the SO2, and then we want to calculate the K and the KP. That's fun. Okay. So first thing that we want to do here is probably calculate the K. Now, if it just says K, we're going to calculate K with respect to what? Any ideas? To pressure or concentration? Probably concentration, okay? Because the KP is for pressure. So let's do this in terms of concentration first, okay? And then we'll go from there. And actually, what we may do is go back and use the equation that we learned at the end of the last section, the one where you can change Kc into Kp and vice versa. So this will give us some good practice on that. But the first thing we need to do here, if we're going to do this in terms of concentration, we need to figure out the concentrations of all of our reactants and products. But that's fairly easy for this one, right? Because we have a 1-liter flask, right? So moles per liter, right? So 2.0 moles in 1 liter is 2 molar, okay? And then 1.50 moles in 1 liter is 1.5 molar. So that's kind of nice. So the fact that we have it in a 1-liter flask makes this a little bit easier. Now, did I leave myself any room? I sure didn't. Okay. I just do not have enough room to do this here. So what I'm going to do is I'm going to open up a notebook page here so that I can actually spread this out a little bit and you can see it a little bit better. While that's opening, could one of you do me a favor and just grab me a set of notes so that I can see what I'm looking at? I should have had one over here, but I don't. Okay. Oh, this is taking a really long. There we go. Okay. Thank you. All right. So again, the question is, we've got the SO2 plus O2 going to 2 SO3. Okay. And get this on full screen here. So the first thing we want to do is probably set up an ice table. Okay, so what I would do when you're setting up your ice table, I would just go ahead and rewrite the equation first. So we've got 2 SO2, and that's a gas, plus O2, which is a gas. That's an equilibrium with 2 SO3, which is a gas. Okay, so then we've got our equation written, and then we just want to do ICE. Okay? at some point we're also going to need to write our equilibrium expression, but we can do this first. It doesn't really matter what order you do that in, and it doesn't really matter if you divide this into an actual chart either. But there it is. Okay, so this 2 moles of SO2, 1.5 moles of O2, and 3.0 moles of SO3. That is our initial concentrations of everything, because we're putting all that together at the very beginning. Okay, does that make sense? So those are our initial concentrations. So we've got 2.00 molar of this, 1.50 molar of O2, and 3.00 molar of SO2. Now I want you to notice something here. Okay, remember how I said that the only place you can pay attention to stoichiometry is in the change row? Notice this does not follow the stoichiometry of the equation, these initial amounts, right? Because we're just putting amounts of these things in here, right? So there's going to be some limiting reactants here. I guess there's only 2 things. There's going to be a limiting reactant here, okay? And there's going to be one that's present in excess. And you might be able to see which is which, but it doesn't really matter at the moment, okay? So then we are also given the equilibrium concentration of one of our reactants / products. Actually, we're given the equilibrium concentration of the product, right? Which is 3.50 molar. Okay. So far, so good? Okay. So then let's figure out our change here. This changed by, went up by 0.50, right? It's supposed to be a decimal point there, not a whatever it might be. Okay, so now we have to think a little bit here, all right? Based on the stoichiometry, because again, this is where we can look at the stoichiometry, is in the change row. How much O2 must have disappeared while 0.50 molar SO3 was appearing? Half as much, right? Because if you look at the stoichiometry here, right? For every 1 mole of this that disappears, there are 2 moles of the SO3 that appear, okay? So this would be minus 0.25. And you have to be careful with your pluses and minuses here. In this reaction, because the product increased in concentration, that means the reactants must be decreasing in concentration, okay? So whatever the product does, the reactants do the opposite, okay? And vice versa. So if this is going down by negative 0.25, what about the SO2? Good. Going down by negative 0.5. Okay, so using the stoichiometry, we just figured out our changes in concentration there. So now we can figure out our equilibrium concentrations of all of these things. 2 minus 0.5. I hope I can do these in my head. 1.50 molar, and then 1.50 minus 0.25. That should give us 1.25. Okay? So there are our equilibrium concentrations. Once this... so again, notice what all that's happening here is we're starting with certain concentrations of our reactants and products. As this thing moves towards equilibrium, the amounts of the reactants and the products change a little bit. Okay, and then once we hit equilibrium, this is our constant concentration of these things. They're not going to change anymore at that point. Does that make sense? Because the rate of the reaction has now become equal in both directions. Okay, so anytime some of the product gets formed, or some of the product moves back towards the reactant, I guess I should say, then the reactant forms more of the product at exactly the same rate. Okay, so these are now our concentrations, and they're going to stay that way. All right, so now to figure out our equilibrium expression for this, we would just say K equals, well, we probably should write our equilibrium expression first, and then we can plug our numbers in, okay? So K equals SO3. If we're writing this in terms of concentration, it'd be SO3 squared over SO2 squared times O2. Are we okay with that expression? Okay. Again, these are all gases, so they all go in the equilibrium expression this time. that might be the one value in doing the equilibrium expression first, is because then you would recognize, oh, that's a solid, doesn't go in the equilibrium expression, and then you can X that out of your ice table if you need to. Okay, so maybe it's a good idea to do the equilibrium expression first. All right, so then we just plug in our concentrations that we found down here. Okay, so we've got 3.50 squared on the top, divided by 1.50 squared, times our O2, which is 1.25. And that should give us our equilibrium constant with respect to concentration. I'm getting 4.36, I think. Is that right? 4.36. Okay. Again, let's just talk about what that's saying. Our equilibrium expression is bigger than 1. Okay? So that tells us that there should be more of the products than the reactants, and that looks about right. Okay, if you look at the concentrations. So that makes sense. So that's our K with respect to concentration, okay? Okay, so far we have found the equilibrium concentrations of O2 and SO2. Okay, so those are two of the things they were asking us for. They also asked us to find the K, which we just found. And then to find the Kp, we're going to have to go back and remember an expression that is on your equation sheet that I am currently forgetting. Let's see, it's Kc, no, it's Kp equals, I feel like it's RT to the delta N. I think that's right. That's supposed to be a delta. I need to look back. Is that right? You got it? So this is right. Okay, okay. So then we can relate our Kp and our Kc at this point. Okay, now what we have right now is technically our Kc. It's with respect to concentration. Okay, remember what I said was you can just write K there. You don't have to write the Kc because typically we find our equilibrium constants with respect to concentration. Okay, so if we want to find our Kp, then you just plug into this equation. Now the delta N is the tough part here. Okay, but we've got, gosh, I need more room. Here we go. That's a great thing about a smart notebook, I guess. So Kp equals 4.36 times R here is 8.314, I believe. No, I'm sorry. Oh, come on. We're doing this with respect to pressure in atmospheres, so this is going to be 0.08206. Okay, so I guess maybe I should bracket this, and then we'll multiply that by the temperature, which I forget what the temperature. Oh, at 600 degrees Celsius. Now our temperature has to be in Kelvin, so we add 273 to that. This is a pretty hot reaction here. 873. Okay. Times the delta N. Now the delta N is the tricky part. Okay. The delta N is the moles of the products minus the moles of the reactants, okay? And so we have 2 moles, now it's moles of gas in the products minus the moles of gas in the reactants, all right? So if we have things that aren't gases, they don't count. Everything in this equation is a gas. So basically we have 2 minus 3 here. Does everybody see that? 2 moles of gas on the product side, 3 moles of gas on the reactant side. So that's going to end up being a -1. Okay? Does that make sense? No, you do. Oh, no, I'm sorry. You're looking at the stoichiometry in the equation. You look at the coefficients in the equation to figure this out. I apologize. Because, remember, we got an excess reactant. If you're looking at those amounts that it gives you in the actual problem, that's not going to be the right ratio, okay? So look at the coefficients in the balanced chemical equation, and that'll tell you. So then you take 2 minus 3, so it should give you minus 1. See, it's good for you guys to be here, because I wouldn't have known that you would have been thinking about that. So then you plug all this in, and this should give you your KP. I'm doing on time. 0.8206 times 873. And take that to the negative first power. So basically the inverse of that, times that by 4.36. And that's giving me a KP of, that seems small, 61, or 609, I guess, if I was going for sig figs here. But again, that seems small. Let me double check here and make sure that I'm using the right R. So that's the one place where I wasn't exactly sure here. The R could be 8.314. I think it's the... Sorry, everybody on the video. Where's the equation? Oh, that's why, because it's not in here. I need to look in the notes. Sorry. What's that? Go with my instinct. Is it 0.08206? Oh, okay, you don't know. Yeah. It should be in our notes from last time. I just need to find it real quick. Let's see here. There we go. KC. And please tell me what the R is. Of course it doesn't. Okay, I'm going to have to look into that because I can't find it here. I forgot that I covered that here and it's not actually in the book. So, the reason I covered it is because I've seen it on a couple of the AP type questions. I need to double check this R and I'll just let you know in class because that seems, usually they're a little bit closer to one another than that. Although I suppose if that number was bigger, then taking the inverse of that would make it even smaller if you used the 8.314. Yeah, so that's, I'm pretty sure that this is right. It's much lower. Okay, yeah, that makes sense. So I'm pretty sure that's it. It's got to be, because we're doing this in terms of atmospheres when we're dealing with the pressures, so that seems like that's the right order. Okay, anyway, last one here. Very quickly, because we don't have a lot of time. Sulfur trioxide decomposes at a high temperature in a sealed container. Initially, the vessel is charged at 1000 K with SO3 at a partial pressure of 0.5 atmospheres. At equilibrium, the SO3 partial pressure is 0.2. Calculate the value of KEQ at 1000. Okay, so again, now we're just doing a simple little ice table here, okay? And basically, we've got the same thing here as we had before. No, I'm sorry, it's a little bit different equation. Very similar. It's actually just the reverse of the equation from above. Okay. And we've got our ICE here. And again, initially here, now you don't, once you get going with these, you really don't need to write all of these, you know, don't need to make this a table every single time, as long as you can keep your numbers straight where they're going, okay? So we've got a partial pressure of 0.500 atmospheres for the SO3, okay? So we're going to do this with respect to pressure, all right? Because they're not giving us enough information to do concentration anyway. But we can assume, it says that it's in a sealed container, so we can assume the volume is going to be the same the whole time, all right? So because that's the case, we can use the coefficients in the equation to do a pressure ratio, just like we would a mole ratio or anything like that, all right? Now, how much of the SO2 and the O2 do we initially have here? 0, right? Because this is a, we're just putting in the SO3 to begin with, and so it's just SO3 in that container, okay? Then it's telling us at equilibrium, the SO3 partial pressure is 0.2. All right, so now we should be able to figure out our change rho here, right? This went down by 0.300 atmospheres. Okay, so then looking at the stoichiometry, the SO2 would go up by also 0.3, and the O2 would go up by half of that, so 0.15. All right, so that's going to tell us our equilibrium amounts, because we started with 0 of both of these things, so that makes it pretty easy. Whoops, it's supposed to be a 1. Okay, so now we have our equilibrium amounts, and basically what you'd want to do here is just plug into the equilibrium expression. So we've got pressure of our O2. I'm doing this with respect to pressure, again, because we're using the atmospheres here. And the pressure of the SO2 squared divided by the pressure of the SO3 squared. All right, so there's our equilibrium expression based on the reaction and the stoichiometry and everything. Okay, and then you just plug in these numbers. So you got 0.150 times the SO2, which is 0.3 squared, divided by the 0.2 squared, and that's going to give us our equilibrium expression. What is it? Okay, we'll go with 0.3375, 0.338, I guess, technically. We're worried about our sig figs here. Okay? All right, so that's that. Next time we get to learn how to use the quadratic formula in chemistry. Yeah, that'll be fun. It probably won't be fun, actually. Okay, see you next time. Oh, there we go.